So can I create just a few exercises to make sure we're up to par? Is that okay?
Yeah.
Everybody? Oh, it's not okay. It's so easy, isn't it? I think when it comes to addition of vectors, scale multiplication, life is a piece of cake. They're just defined component-wise. Well, I should say, addition of vectors is just component-wise addition. Scale multiplication of vectors is just component-wise multiplication of the scalar. Life's a piece of cake, right? I do think, however, maybe we can talk about maybe a multiplication process where I'm multiplying two vectors, and I've got one. And I come to class very nervous. You know I don't like reading out of the book, but I'm going to read out of the book. Sorry, maybe you don't know that. You don't know me. But for those who do know me,
I'm scared.
I don't like going
Are you talking about dot product? Or
Yes.
dot?
So here I go. Page 704. Very first sentence in section 11.3. Guided by some example he mentioned in the past about force, we give one definition of the dot product. Then an equivalent definition is derived a little bit later in the same section. Does that sound awkward? Anybody? Yeah, I think it should. It doesn't make sense in mathematics to define something one way and then say, let me define it this way. I think whatever said the first time around should be a consequence of the second one, or vice versa. Now, if you take a peek at his very first definition in that big gold box on the page, on the top of page 704, I don't like it. I'm sorry. I don't mean to come to class and say nasty things about the book, but I'm very uncomfortable saying that my definition of the product is what he has on that page. I'll mention what he has on the page. I'll even drag it out of thin air for you today. I just don't like calling it my definition. I think it's a geometric consequence. But you probably don't have your book with you today. You may not see it in your head. I'll put it on the board in a few minutes. For that, let me give a formal definition of the dot product. Mine. So, definition. Let A be two vectors. I'll even give you the components. The dot product of A and B. In other words, a whole new process for multiplying vectors together, I will now define as being nothing more than the product of A1 and B1. The product of A2 and B2, and then I'll add them together. You guys, this is a man-made definition. This is not in here for me to prove. And you can say, well, who the heck cares? I promise I'll talk about this dot product. We'll see some consequences today. Before I do, though, understand that I'm really multiplying two vectors together, but I'm not getting a vector. I might say as a mathematician that when it comes to this process of multiplication, there's no closure here. I don't get another vector. For those of you who've already taken Math 33, you understand that language. Is there anybody in this room who's taken Math 33 already? Catherine. Alex got it. So two of us. Oh no! I don't like my definition. Shoot. These are vectors in two space. What are the vectors in three space? Anybody?
Same thing.
Same thing. Just add another term, and it'll be the product of A3 with B3. Are you guys there? By the way, am I getting confused? Am I confused by notation? I got a dot here and a dot here. Is that ambiguous in terms of not knowing if it's multiplication of vectors or multiplication of scales? Yeah, I don't think it's confusing. I think it's clearly understood with notation. I'm combining two vectors by an operation, so it's understood that that's a dot product. And it's understood that since these two represent real numbers, that that's multiplication of real numbers. Oh no, you guys have made another mistake. I don't need to sit here stuck in 2- and 3-dimensional space.
What you're saying is that it works all the way through.
Absolutely. That's exactly what I'm saying. So somebody help me with this. A bar dotted with B bar can be interpreted as, pick a letter.
C bar? No,
No.
C.
N.
Better letter. A. How about S from the Greek alphabet? So we're summing together. Gosh, I'm hearing my voice too much. A sub I.
Is E sub I from I to N?
Beautifully put. Much more concise notation for that. So, examples. You guys, a really silly example, because you're not going to care why I'm doing this yet. But if I ask you to consider A bar being this, and B bar being this, then I maintain the dot product between A bar and B bar is nothing more than the sum of these products. Is that a 1 times 3 plus negative 3 times 1 plus 2 times 5? I'm sorry, maybe this example insults your intelligence. I know it's a simply arithmetic question. I've gone as far as, that just be a 10. Okay, so it's a number. But keep that in mind, it really is a number, not another vector.
Following meaning fall? What does that say?
Is the following meaningful?
Oh, okay, okay.
Are you adding a scalar with a vector?
Thank you. And I think that for that reason it doesn't make sense. I don't think this is meaningful. I don't think I get a single thing because I can't add vectors to scalars. Dot product, 2 vectors, a scalar. Multiply scalar by 3, another scalar. But scalars cannot be added to vectors and be meaningful. Do you guys agree?
Yep.
Yeah, it's meaningful. What do you get in the end, a vector or a scalar?
Vector.
You get another vector. Yeah, that's meaningful. I just get a scalar divided by another scalar, which is just a scalar. Everybody there? Ah. By definition, that's not an eraser. Oh, what's all this? Anybody?
I can't see it.
Blur's on the computer. This isn't from any of you guys?
No.
Somebody came in here and left their account open. What fun we can have with that.
Talking like a financial account or a social account?
I don't know, it's Cliff Myers, I think. Left it on and somebody came in and redid his webpage and rewrote the name with Cliffy. I don't know if that's true, but that's what I heard. So everybody, let me do this. Let me commit to the following. Because I think when it comes to the dot product, there really is a nifty geometric consequence of having such a product. And to demonstrate this, allow me to play. And just because I want to be able to draw and talk about this smoothly, can I just restrict myself to 2-dimensional space? Because any higher dimension is going to have the same quality. I want to consider this vector u bar and this vector v bar. And I want to talk about the dot product. So would you guys agree with this? If u bar is equal to a1, b1, excuse me, I misspoke. I meant a1, a2. I'll be consistent. You guys check out what would happen if I took u bar and dotted it with itself. Don't I just simply get this?
A1 squared times
Yeah, I agree with that. I just get a1 squared plus
plus A2 squared,
a2 squared,
which is the magnitude squared.
which is the magnitude of a bar, because the magnitude of a bar is nothing more than the square root of a1 squared plus a2 squared. You guys
A bar,
What's that?
isn't it U bar?
Oh, sorry. Different letter. I want you to cue on another mistake I meant to make. That one I really made. Do I have a mistake?
Wouldn't it be squared?
Yeah, I can't just take the square root of something, I gotta compensate for my action. So if you guys don't mind, I will now undo the square rooting. So in the end, if ever you see the dot product of a vector with itself twice, you could, if you so choose, interpret it as the square of its magnitude, if you so choose. This is the time for you guys to attack me.
Why would you do that?
Yeah. How's that useful?
You know, if you already knew the magnitude of the vector,
Okay.
then certainly just squaring that magnitude is the same thing as dotting the vector with itself twice, if you want to consider the dot product. That's a lousy answer. Can I give you a better one? Because I want to commit to some playtime. And I'm going to use that. I'm going to exploit
Okay.
it. So I'm ready to exploit it. Does anybody have another nifty name for this vector?
V bar minus U bar.
So V bar minus U bar. Do you guys agree? You can double check, see if you made a mistake. These two vectors in black and in blue are hooked up head to tail. And therefore, when I add them together, I should get V bar. But adding these together, the U bars cancel out. I'm merely left with a V bar.
Wouldn't the arrow be going the other way on that?
See, I disagree. I think the arrow going the other way would be a U bar minus V bar. So, Brad, let me show you how I think.
Okay.
Since this blue one is really V backed up by U, I'd write it this way. Or again, if you think I made a mistake, cover this up, don't look at it. Since these two are hooked up head to tail, I think adding these two together gives me the resultant vector. But U bar plus V bar minus U bar is just V bar. Oh, thank goodness. That's what it was originally labeled as. So I haven't made any mistakes.
Okay.
Check this out. Since I now have a nice nifty geometric triangle, then somebody tell me what the Pythagorean theorem says about this triangle.
V bar equals V bar squared plus this other vector.
It would, I agree with that, if it were a right triangle. But you guys see my point? I don't have a right triangle, so I guess the Pythagorean theorem doesn't say anything. But if I ask you to cue in on this angle, the angle theta in between these two vectors, you probably can use an extension of the Pythagorean theorem, which is log cosines. After all, the Pythagorean theorem is a particular case for log cosines, isn't it? So by the law of cosines, if I so choose, I can state this is a relationship among the three sides of this triangle. Namely, that the length of the blue side, oh shoot, that's a vector. I guess talk about its length means talking about its magnitude. I've got the magnitude of V bar minus U bar twice being equal to the sum of the lengths of the other two sides. That would be the magnitude of U bar and V bar squared. Minus twice the product of the other two sides, or shall I say the magnitudes of the other two vectors, times the cosine of the angle in between, which I labeled in my picture merely as theta. However, relative to what I just erased on this middle board, you guys, Bradley, I'm finally getting to an application of that silly thing. I think I can reinterpret this. That is to say, the magnitude squared of that vector as a dot product of that vector with itself. I said dot product. Ay, ay, ay. And I think what that gives me on the right-hand side is, do you mind if I skip it? I just skip the right-hand side. It's just that dot products do distribute. I get to typical operations or typical qualities operations with dot products because they're simply defined in terms of scalar multiplication and addition. Then I maintain I've got a V bar dotted with itself twice, minus U bar dotted with V bar, minus a V bar dotted with a U bar, and then finally plus a U bar dotted with itself twice. And this is equal to stuff. But you guys, do you mind? I mean, V bar dotted with itself twice could be also interpreted as V bar's magnitude twice. And I guess with these two terms, oh shoot, they look different, darn it.
Well, it is true. It's
You could.
is it commutative?
Perfectly put. You've got the right word. I think this operation is commutative. It's clearly commutative because take a look at this product. You guys, let me take a look at this product. Now, when it comes to multiplication of vectors, what do you think I'm going to say? Nothing. These aren't vectors. These are
Scalars.
real numbers, or scalars. Since they're real numbers, we already understand that multiplication commutes. And since multiplication commutes with real numbers, I guess trivially what that really means is that dot products commute as well. You guys yell at me if I'm talking my way through this too fast. And I maintain, I can therefore rewrite these two terms as 2 times the dot product of u bar and v bar. Oh, by the way, over here, check this out. That's u bar's magnitude twice again. Did you guys see why I'm going through all this?
Yes.
So where am I going next?
Gonna cancel
Stuff.
Yeah, cancellation all over the place. After all, the u bar is magnitude squared, cancels on both sides. Same with the other vectors, magnitude squared as well. Do you guys mind if I cut to the chase? Now that they're canceled, let me divide both sides by -2, and I maintain there's a new interpretation of a dot product. Namely, the dot product of, I'm using A's and B's again, sorry. I'll be consistent.
So you just
I
end
think
up
in
with
dividing
one.
both sides by
Yeah.
-2, I see that the dot product between A and B, or U and V, I don't care what you call them, could be interpreted as nothing more than the product of their magnitudes times the cosine of the angle in between those two vectors, u bar and v bar, or sorry, over here, a bar and b bar. Here's where it comes into play with what I said about reading out of the book. This is the alternative definition the author gives. Actually, he gives us geometric interpretation as definition, calls the other one that I gave you up here a definition, but then proves this one from here. That means it's not a definition of mathematics. It's a theorem. I just chose to start off with an analytic definition, one that's not quite as geometric. I think this is a big deal. Because I think everything I've said so far is so darn meaningless. What the heck, it doesn't matter that you have a dot product. Who would ever take a dot product? Well, look at that relationship. I think it says everything. Because I think the dot product, therefore, can be interpreted as saying something about the angle in between those two vectors. In addition, what would happen if the angle in between two vectors is something special, like 90 degrees? What's the cosine of 90 degrees? 0. Therefore, the entire right-hand side is 0. Therefore, the left-hand side is
0.
0. I've got a two-way theorem. So first direction. If the angle in between two vectors is a right angle, if the two vectors are perpendicular, the dot product's going to be 0. But if you compute a dot product between two vectors being 0, then you can conclude that the angle in between those two vectors is a right angle. Are you there? By the way, this works in any dimension. By the way, if I had some nifty way of, I don't know, generalizing vectors, just look at their bare qualities, putting on a pair of special mathematical glasses, I only see the underlying behavior of vectors. Maybe there are other things in mathematics that have the same quality as these dot products, and there are. You'll see plenty of them next semester in Math 33, if you take Math 33. Well then, what do you think I can say about this? What do we do with my erasing? Oh. And where am I at? Example number... Is it 3? Sorry, I'm drawing a blank on it. Anybody?
What's that?
Determine the angle between...
Oh, that's an angle?
Yeah.
So is that a mathematical way of writing angle, or is that just something you just drew?
Yeah, I do this all the time, don't you guys? Or your high school geometry teacher probably does this all the time. Okay, so I'm different. How do I hang out between? Anybody? Yeah, just use a dot product, or at least a geometric interpretation of dot product. You guys, I'm just going to write down the dot product of these two. I'm writing too much. I'm writing too much only because I assume you guys haven't seen this before. That's why I'm taking time on the clock. Oops, hold it. I can write one even. Equals a product of the magnitudes. Times the cosine of the angle in between. Ah, shoot, look what I just did. I created one equation, one unknown. Piece of cake. That's all. Does that give me a... Oy, oy, oy. Is that 16?
Yes.
Is that root 14? Again, for those who don't know me, I'm being honest. Just double check my arithmetic. It needs to be checked. Is that a 35? I said 35. And cosine of theta. So you guys cut to the chase. What's theta? You took way too long. What's theta?
Well, who has a calculator?
No, no calculator. You're on a desert island. There's no calculator. What's theta?
Inverse sine of.
Inverse cosine.
Inverse cosine, sorry, of 16 divided by root 14.
I agree completely. You guys can agree?
Well, what's root 14 times root 35?
It's root 14 times root 35.
Well,
And by the way, Brad, this example.
how do we know that that doesn't simplify without actually?
Oh, piece of cake. That's a product of only two primes, 2 and 7.
Okay.
This is a product of.
You can take a 7 out.
You're right, Brad. When I did this in my head, when I put these numbers down, I factored incorrectly. He's right and I'm wrong. This does simplify. I'll be quiet. 16 over 7
Root
roots.
2 times
2 times
5 is 10 root
5
10.
is 10. Good. I'm glad you stopped me.
Alright.
The feels there. Oh, by the way, that says something else about these two vectors. So Pan can say something relative to what I have on the board.
Cosine inverse of a positive number
Thank you. Since this is a positive number, that means the angle is
between negative 180 and 180 degrees. No, hold on.
I was hoping you'd say something different, between 0 and 90.
Right.
And I think if this ends up being a negative angle, it just simply means, if you end up generating something that's negative on the inside, that just simply means your angle is between 90 and 180. Why are you stopping at 180?
Because
No,
when you're doing the inverse function, that's the.
When you're evaluating the inverse cosine function, the output's necessarily going to be an angle between 0 and 180. I agree, that's why you stop at 180. So, I maintain this. Got a dot product that's strictly positive. I think in the end that implies the angle in between the two vectors is going to be acute. I think if the dot product ends up being so small that it becomes 0, the angle in between is 90 degrees. And if the dot product is negative, it means the angle is even larger. It's larger than 90 degrees, but less than 180.
Why does it have to be less than 180?
Because the output of the inverse cosine function is an angle between 0 and 180.
And you can't have two vectors that have a farther angle apart than directly away from each other.
True, because then you can talk about the other angle. Yeah. Eric, do you see why the inverse cosine has that restriction?
No, it
Oh,
doesn't
really?
make sense to me.
Okay. Just ask.
I was waiting until he finished talking.
Could you repeat that last sentence about this.
Yes.
Okay.
I'm simply saying this. If the dot product of two vectors as a number ends up being positive, it necessarily means that the angle in between is going to be between 0 and 90 degrees.
Positive, and you stated it as being positive.
My apologies. No, I still correct it.
Okay.
If the dot product, this number right here,
This number, the 16 or whatever it was. Right.
the 16 in this example, yes.
Okay, so the actual.
If this dot product ends up being positive, I think that means the angle between
Will
the
have to
two
be
angles.
positive. Okay.
But Linda, I said this. If the dot product ends up being negative, then I think the angle over here is between 90 and 180. Eric, check this out. Now you guys know that when it comes to inverse functions, I can create the graphs just by taking my function and reflecting through the line y equals x. And if I reflect this curve through the line y equals x, I get something that's not a function. So bottom line, there is no inverse cosine function. So what I will do instead is just take a subset of the domain of my cofunction, which is all real numbers, say from, I don't know, how about from here to here? From 0 to pi. And I'm just going to take that one blue piece of my cosine function, which by the way is a one-to-one piece, and spans all y values from negative 1 to 1, and reject the rest. So if I restrict the domain of my cosine function from 0 to pi, or 0 to 180 degrees, then I've got a one-to-one piece of my cosine wave spanning all desired y values, and I can reflect that through the line y equals x, get a function, and that's what I'll refer to as the inverse cosine function. But it'll only exist when I restrict my domain to something, Why did I choose 0 to 180 degrees? It was convenient. By convention, I'm serious, by convention, we choose that piece. I could have chosen a piece way out here. But that's a 1 piece spinning a y values of -1 to 1. But so that what I'm discussing or thinking is the same as what somebody else is discussing or thinking halfway around the world. We all, by convention in mathematics, choose the same 1 piece.
Okay, that makes sense.
As long as you're happy. Oh, let's talk about some qualities of dot products. I think I mentioned some already. You guys, we've already mentioned this one. U bar dotted with B bar is equal to 0 if, and only if,
Yeah, between the zero.
yeah, the angle in between is going to be, you said 0, but you meant, what? 90 degrees or pi halves. Secondly, I do think you and I have already shown that if I dot 2 vectors like this, order is unimportant. In other words, the dot product is an operation between 2 vectors, commutes. I maintain that if I take a scalar times, hold on, I'm getting too slow again. If I take a scalar times u bar, and I dot it with a v bar, what do you think I should get? Scalar what?
C times the dot.
You mean like this?
Yeah.
If I asked you to prove it, could you?
Yeah, sure.
I'm hoping you can. Actually, can we do it real quick? Middle board. If I take a scalar times v bar and dot that with v bar, I think what I'm really doing is looking at the sum. By the way, I never told you what dimension space am I living in, did I? Let's assume
Doesn't really
it's,
matter.
it doesn't matter, but let's assume it's n to be general. Then I think I've got the sum as I place in of my, gosh, how does this go? Symbol by symbol. Symbol. Symbol.
Sum. No,
Parentheses.
okay.
I feel so alone. C.
U1.
Yeah, I don't know what you want to call it. A sub 1. You said U sub 1. That works fine.
Couldn't you just,
C sub 2?
You really meant.
B.
Yeah, times B1.
Wait.
I'll wait.
Okay, I get it. Never mind.
Good. Eric?
it seems more logical just to factor the C out.
But wait a minute. That's what I'm trying to prove.
Oh.
I'm trying to prove the factor now.
Oh, okay, but isn't, we can just, we should already know that, we've taken 31. I mean.
Really? Let A be a vector. Did I misspeak? I said let A be a vector. I meant let A be a matrix. That's not true. I think quite often in mathematics I get systems for which that does not apply.
Okay, but in this time it does.
Yes, that's true, but I'm asking you to prove to me that it's true. I know it sounds silly, Eric. I think what you're trying to get at is that I'm trying to prove the bloody obvious.
Yes, yes.
It's just that since I'm the one who gave you a man-made definition of dot product, then I think this is a consequence of that definition, and I can prove that it holds true.
Okay.
So, you guys, let me prove it. I want a yes or no answer. Is that a real number?
Well, constant times a real number.
Is that a real number? Is that a real number? They're all 3 real numbers. Oh, but shoot, in the real number system, for the operation multiplication, we got something really nifty working for us, namely the associative property. It allows us to rewrite what's within the sum as nothing more than C times the product of V1 and V1.
Okay.
What's next?
Did you factor C out of the sigma?
But you said as a question. Restate that, but be assertive.
Can you take like C out of the sigma?
Yeah, you still ask it as a question. I don't just say.
Just take it out.
Okay.
Oh shoot! Did I make a mistake? Is that really legal?
Well, it's not being affected by the sigma, is it? Let's see.
My pen's drying out. Oh, that's a question. Is that really legal?
Also, shouldn't those,
Yeah, it should be eyes, not ones,
So sorry, you guys.
because it's raining.
My goodness. I'll fix it.
Okay. Yeah.
With the sum there, you'd be able to factor a C out of everything.
Why?
Well, because
What
C
is
is,
factoring?
C is gonna be a common factor to all of the terms.
What is
that you're
factoring?
adding
All
together.
you're saying is that C is multiplying by every single step in the
Man,
problem.
you guys are using a lot of words. Make that more concise.
Okay, C multiplied by numbers.
Can you make it shorter?
C is a constant.
I mean, in a previous step, we assumed
There's no
because we were dealing with real numbers that
Yes.
we could pull the, we could apply the associative property of real numbers.
Why are they different here and here?
Yeah, I know, but
Distributive.
as an extension,
That's it. She said we're applying the distributive property for multiplication over addition.
yes, that's true.
Well, in the reverse direction, but isn't that really what factoring is in Math B?
Yeah.
Oh, by the way, I didn't finish, darn it. I meant to conclude that C is being multiplied to, the dot product of U bar and V bar. We proved what we're gonna show. You guys, have I used it symbol in class? I haven't, sorry. This is my mental hiccup at the end of a proof. I don't know what you guys are used to, you've probably seen this. Quadratum demonstratum. Latin for that's what I want to demonstrate.
Quad, what?
Eratum demonstratum.
Quad demonstratum.
Quad.
Oh. Where's the E come in?
What's that?
You said quad demonstratum, what's the E?
Quad eratum demonstratum.
Oh, okay. And what's the little squiggly?
Like,
Like, what does it mean?
This is just a symbol, a man-made symbol that often mathematicians will use at the end of a proof.
Oh.
It's
so
my mental hiccup.
It's like the watermark.
I think it's a little different than a watermark, because watermark is just light in the background. This is about bold pronouncement that I finished proving what I wanted to show.
Oh, okay.
Maybe you guys are used to high school stuff? A lot of high school teachers use that.
I've never seen
Yeah,
it.
I've never
Never
seen
seen
that.
Don't we look at this? Which was what we wanted? Textbooks often put this at the end, like just a rectangle. Anyway, just so you know, that's my mental hiccup.
What does the rectangle mean?
It's just a simple lot of textbooks will use it instead of mine, or instead of this, or instead of this. It's just, we prove what we want to show.
And maybe it uses
Okay.
less.
Why
ink
did
or
it choose a
something.
rectangle? I have no clue.
Maybe it uses less ink or something.
Good point, maybe use less. I can see that. Oh, you guys, is there anything else? There is. Hold it. Shoot. Okay, you can prove this one. If you add two vectors, U bar and V bar, and you dot it with W bar, you will get U bar dotted with W bar plus V bar dotted with W bar. In other words, dot products distribute over vector addition, if you want me to say it in English. Now you guys, this semester, I'm not gonna sit here in class and pound my fist on my table demanding you know in detail each one of these four properties of dot products, but if you just give me one more semester, I will demand it. And you'll start referring to a general dot product as a
Oh, inner product?
inner product, yes, and talk about those properties. Jeepers. One more example. Shoot, I guess I won't stop at one more example. Let me give myself some room. You guys, I'm sorry if I'm stalling with my thoughts. I'm just really, really tired. UFO? It's a car.
Oh, sorry.
Jeepers. You guys, if I exerted a force on my car of 100 pounds, and with that force I moved it 10 feet. Oh, but next time I exerted that same force of 100 pounds on my car, but this time I moved it 100 feet. Which scenario, the first or second, is it the case that I'm applying more force?
Second case.
Which one?
Neither, it's the same.
Did
It's
you
the
guys
same.
agree the answer is neither? Only because the force is the same. But I think I need to make up something out of thin air to distinguish between these two scenarios, because I think I'm gonna be a heck of a lot more tired down here than I was up there. So even though it's the same force exerted to get the car moving, since there is a difference in these two scenarios, can I make up a word out of thin air? This is not a theorem. When I say making up a word out of thin air, I'm saying I'm making a definition, a man-made definition. I will multiply the 100 by the 10, or the 100 by the 100. I'll multiply the force by the distance, so that these two quantities are different for those two scenarios, so that this whole new number I'm making up distinguishes between those two scenarios, and I'll assign a name to it. I'll call it work. And again, this is not a theorem. It's a man-made definition. Work is a product of force and distance. It's just that for you and I, we're going to consider a force a vector, we're going to consider distance a vector, and we're going to assign the dot product of those two vectors to represent work, just like with scalars. So I maintain if you really wanted to, you could also compute the work done with a certain force for a certain distance by looking at the product of magnitudes and multiplying by the cosine of the angle in between, if you so choose. Are you there?
What if
Yes.
it's not an angle of the force?
Say that one more time, I'm
Or
sorry.
just like you apply the force at an angle instead. So,
Oh, you mean like example number 5?
oh wait, never mind. I just answered my question. It's going to be like the cosine of the cosine theta of the angle times 100 pounds, and then
If you want it to be, yes, but you can also interpret it with the original definition of the dot product. You've got a choice, and that's why I'm putting both on the board. Choose whichever one makes more sense to choose. Look at this picture. I got a crate. I want to drag on the floor, and I want to drag it 15 feet. Excuse me, can I change that? Can I refer to 15 meters? And I'm applying a force, but I'm not laying on the ground. Standing up. And I'm pulling with a force of, say, 25 pounds. Excuse me, I said 25 pounds. I want to be consistent with my units. 25 newtons. Oh, but the angle I'm making is an angle of 30 degrees. Then how much work is being done to drag this crate 15 meters if I have to apply the force at that angle from the ground? Well, I think the work is just computed by looking at the product of their magnitudes times the cosine of the angle in between. Does that just simply give me, I have no idea what that is.
324 point.
3 over 2 times 15 times 25.
I know, 50 times 25, I'm just so tired. 375, thank you. Times the cosine of 30 degrees, you guys get your
3 over
calculator?
2.
Good, no calculator. The cosine of 30 degrees is a piece of cake. What are my units?
Newton meters?
Yeah, I'm not sure what the units are. Newton meters works.
Well, that would be what it is.
What's another name for Newton meters?
Joules.
Joules, so you could have said joules as well. I'm just saying we have a choice. Is that okay, you guys?
If you want to leave it in exact form, you could convert it to a decimal if you're willing to goof around with that root 3.
Ooh, it makes me shiver. So I'm in three-dimensional space. So for me, in this example, to compute the work, let me go and consider the magnitude of my first vector. But you guys, the magnitude is the square root of
1 squared plus 2 squared plus 3.
It's not.
12 squared.
4 plus 1.
we
It's not just the force.
yeah, why go through all this work? Oh, no pun intended. Why go through all this? Why not just simply look at straightforwardly at the dot product? Ah, piece of cake. I think the work done is just 1 times 3 plus 2 times 5 plus 3 times 7. Do you mind if I stop? You can finish your notes. Oh no, you guys, everything I said doesn't seem to jive really well with the mathematics you've learned so far in your mathematical career. It's because of what I said initially. Jeepers, dot products is a way of combining two vectors to generate something that's not a vector, a scalar. So if you guys don't mind, can I make up a whole new product